Good afternoon. I'd like to welcome you to the webinar on ratio and proportion, increasing in unequal ways. What I would like to do this afternoon is to give you a different perspective on how to look at ratios across the grade levels, in addition to looking at building into a proportion. Dr. Frank Ardella couldn't be here this afternoon, so I will be the one that will be presenting this webinar. The objective of the webinar this afternoon would be to develop an understanding of the difference between a ratio and a fraction. That seems to be a very confusing factor for students to be able to distinguish what is a ratio and what is a fraction. So this afternoon, that is one of my main objectives, to distinguish between a ratio and a proportion, in addition to looking at a ratio as a set of comparisons of sets. So this would be a different way of looking at a ratio, of looking at it to develop that concept of a ratio as a comparison of sets. What I would also like to introduce you to this afternoon is a concept that Frank and I have thought about as a way of bringing together the mathematics. First to do it kinesthetically, then to tie in the language. From there, bridging it to the connection of connecting all of the factors, and then lastly, the symbolic. So we call this the model of four. It's bringing together different components and presenting it to the students in a way of showing them various ways of looking at the mathematics, kinesthetically, using manipulatives, writing and what are we talking about, the language, making the connections to concepts, and of course, the last but not least, the symbolic. Math is a language of symbols, so bringing this all together in the symbolic. When we look at the mathematics of topics in grades K to 8, we look at addition, subtraction of whole numbers, multiplication, division, whole numbers, fractions, decimals. We never look at really truly the concept of ratio and proportion. But ratio and proportion are an important mathematical tool. It's this understanding that helps students solve a variety of problems across the grade levels. It is an underlying thread, but it's not thought of as being one of the major topics. So again, as I stated before, one of the important things that I would hope to get through this webinar, or to have you understand at the end of the webinar, is the importance of ratio and proportion and how to look at it. So we look at these quantities as playing an important part of being able to solve mathematical problems, in addition to looking at our traditional topics of the whole numbers, the fractions, and the decimals. If we look at some of the research on ratio and proportion, it has been viewed that proportional reasoning is a pivotal concept. It is a culmination of what the children do in grades 3 through 8 in looking at being able to reason proportionally. As it's stated, is the capstone of children's elementary school arithmetic. We look at it as being part of arithmetic. Research has also shown that proportional reasoning is an underpinning of being able to do algebra. And as it states, it is the cornerstone of all that follows. That ability to do proportional, or have that sense of proportional reasoning and to understand it, is very important in the higher and advanced math topics. So as I stated before, what I would like to do today is give you an understanding of the importance of ratio proportion in grades 3 to 8. I think one of the major concerns that children have, or major stumbling blocks, is that they're not able to distinguish between what is a fraction and what is a ratio. That is an important concept for them to be able to distinguish what is a fraction and what is a ratio. So what is a fraction? Let's think about what is a fraction. In the last webinar, we talked about what is a fraction. Based on how we teach it, we tell the children that we are going to take an object and divide it into equal parts, and the fraction will represent how many of those parts I've taken or how many of those parts are left. So a fraction is a number. It is a number that names the part of a whole or a part of a group. It's a part of a whole. We take an object, divide it into equal pieces, and we want a part of that whole. So we're looking at taking parts of a whole, dividing it again into equal pieces. That's a fraction. We talk about parts to whole. Same units. We talk about taking a pie and cutting it into 8 pieces, and I have one of those 8 pieces. I have 1 out of 8, 1/8 of the pie. So a fraction, again, is taking an object or a group and dividing it into equal pieces. I'm talking about the part to the whole, the part to the whole. Okay, we talked about what is a fraction. A fraction is a part to a whole. Well, let's look at what is a ratio. How is a ratio distinct from what is a fraction? A ratio, again, is a comparison, but this time of 2 quantities where the quantities do not have to be of the same units. Do not have to be of the same units. Suppose I have 5 brownies and 3 cookies. I can say that I have a ratio of 3 to 5. 3 cookies to 5 brownies. So my ratio is 3 to 5. I'm talking about cookies to brownies. But suppose I state now that I've taken 2 of my brownies and I gave them to my friend Sue. So I've given Sue 2/5 of my brownies, and I am left with 3/5 of my brownies. I'm talking about a part to a whole, where in my ratio, I stated before, I have 3 cookies to 5 brownies. I'm talking about cookies to brownies. So a ratio is a comparison of 2 quantities where they do not have to be of the same units. Another distinct difference between a ratio and a fraction is that with a fraction, I can add fractions, I can subtract fractions, I can multiply fractions, and I can divide fractions. With a ratio, I cannot add or subtract if it's different units, if it's a comparison. So a ratio can be a part to a whole, but it can also be part to part. I'm talking about 3 to 5. 3 cookies to 5 brownies. The standard joke is that every fraction is a ratio, but not every ratio is a fraction. So when we look at it, we notice that with ratios, as we will see later on, they have multiplicative properties, not additive properties. Ratio could also be miles per gallon. We're talking about miles to gallon. I went 50 miles on 1 gallon of gas, so it's 50 to 1. I'm not talking about a part to a whole. I'm talking about a comparison of 2 quantities. Also a rate, 50 miles per 1 gallon of gas. I walked today 2 miles in 1 hour, miles to hours. So when we look at making a distinction between a fraction and a ratio does not have to be part to whole. It can be quantity to quantity where the units do not have to be the same. That is the major distinction between a fraction and a ratio. If we look at the Common Core State Standards mathematical practices, of which there are 8, we look at the first one, of which states, make sense of the problem. An important part of being able to solve these type of problems with ratio and proportion is to make sure that the students understand that what they are looking for is a ratio in many of the problems and not a fraction. Right? Maybe comparing 2 different quantities, not a part to a whole. So that making sense of the problem is very important when we start looking at how to distinguish between, am I talking about a fraction or I'm working with a ratio? What we're also going to do this afternoon is looking at modeling the ratios, or starting to get students to understand, the children to understand how to look at a ratio. I'm modeling this mathematics using the manipulatives to be able to come up with that underlying concept that is a comparison of two quantities where the units do not have to be the same. So when we start looking at these principles, it's important that we start to take these principles and integrate them into our lessons so that the students are getting to understand the underlying concepts. If we continue to look at the mathematical practices, one of the important ones here is look for and make use of structure. So the students should be able to look at the problem and state, am I looking for a ratio? Am I looking for a fraction? How am I going to solve this problem? So looking for and making use of structure is another important mathematical practice that we need to start to have the children understand when we're doing our lessons. We have to be able to integrate, as I said before, integrate the strategies into creating problems that the students could do. It's not going to be possible to put all of these 8 practices in every problem or every lesson that we do, but I think that in the elementary grades, making sense of the problem, being able to reason, modeling, using the appropriate tools, and look for and make use of structure are very, very important when we start to create the tasks for the students to be able to do, so that they could look at these tasks and be able to come with some sense of what am I really supposed to be doing in order to solve this problem? What are the tools that I have so that I can solve the problem? The Common Core standards in mathematics are built on 3 principles: coherency, rigor, focus. They're saying that these are the major components behind the mathematical standards. So if we look at the mathematics proficiency, conceptual understanding, comprehension of the mathematical concepts, operations, and relations. Procedural fluency, skills to carry out the process of being able to solve the problem using the appropriate tools. That's the rigor. That's the rigor in the Common Core standards. Having a conceptual understanding and the procedural fluency to take that understanding and solve the problems using the process to solve it. The coherency is just looking at tying all of the concepts in the tasks across grade level, building. One of the important things about the Common Core standards, or the essentials of why they're so important, is that we're trying to build coherency as a building block. You do something in grade 3 and then you build upon it in grade 4, and it's not doing it a mile wide and an inch deep. It's opposed to looking at the depth of building, the understanding and the conceptual understanding of how these topics of fractions and decimals and percents and ratios all tie together. That's the coherency. The focus is that the standards are supposed to be very focused and not all over the place. So if we look at the mathematical proficiency, that conceptual understanding, procedural fluency, is the rigor of how we're going to take our standards and implement them into the classroom. The last 2 mathematical proficiencies, as defined by the National Research Council, are adaptive reasoning, where we're basically having the students try to really thought-provoking explanations of and justifications of why they solve the problem. If you've reviewed some of the sample problems that Park has put out, some of the problems will ask the students in an open-ended question, not only to do the procedural part of the problem, but also to explain their reasoning. So that adaptive reasoning is an important part of our standards, and we need to start looking at developing problems that not only just go through the mechanics of the problem, but asking the students to explain why they did what they did. And I think that also helps us in a formative assessment of being able to look at what do the students really understand. Do they really have a total understanding of the concepts, the underlying concepts of the problems? So that adaptive reasoning is an important part of what we need to look at in all of our tasks. And then, of course, the product disposition is really just the habits of mind, getting the students to just do this out of, being able to just do it. It's a habitual inclination. I totally understand that I feel comfortable with. It's that habits of mind. Before grade 6, you will not find the word ratio in the Common Core standards. But before that grade, before grade 6, the students are working with fractions. So they should have a total understanding of what is a fraction, how to work with fractions. That's the coherency piece that's going to play an important part. Understanding fractions before grade 6 and taking some of those concepts of fractions and now moving them through to what is a ratio. They also can understand a ratio as being a rate sometimes, that word rate as being generated through some of the differences of how things are growing. So having these concepts and the fluency of these concepts set the foundation for being able to have an understanding of the difference between a fraction and a ratio. So we're going to look at now, as we move on, how to implement what is a ratio and how it will differ from a fraction. What I'm going to show you now is a video of a way of what we think might be a way of looking at how to introduce the concept of a ratio. So I want you to take a moment. We're going to look at this video of an introduction of using manipulatives to introduce a ratio.
We are going to look at how to match things in an unequal fashion. In this example, we're going to use apples and oranges. For my apples, I am going to use red chips, and for my oranges, I'm going to use orange chips. And in this case, we're going to match 2 apples and 6 oranges. Let's do that again. Again, the way I'm doing it is I'm going to match 2 apples and 6 oranges. So now I have 2 sets of 2 apples and 6 oranges. I have 1 here and I have 1 here. But I could also say that I have 4 apples and I have 12 oranges. Let's do it one more time. I'm going to take a set of 2 apples and I'm going to take a set of 6 oranges because we are giving out the apples and oranges as 2 apples and 6 oranges. So now I have 3 sets of 2 apples and 6 oranges. I have 1 set here, 1 set here, 1 set here. Or I can say I have 6 apples and 6, 12, 18 oranges. Now what happens if we want to say that we want 14 apples? So let's put 14 apples down. So now we have 2, 4, 6, 8, 10, 12, 14. The question is, if we're handing out oranges and apples at a rate of 2 apples and 6 oranges, how many oranges are we going to have if we have 14 apples? Well, let's match up the oranges to all the apples that we have. So we're going to take another set of oranges and put it with this set of apples. We're going to take another set of oranges and put it with this set of apples. We're going to take another set of oranges and put it with this set of apples. And finally, we're going to take another set of oranges and put it with this last set of apples. So now we have our 14 apples, which we had before, and now we've matched up each of these sets of apples with 6 oranges. And the question is, how many oranges do we have? Well, we have 6, 12, 18, 24, 30, 36, 42 oranges. Another way of looking at this is we have 7 sets of 2 apples. That's going to match up with 7 sets of 6 oranges. 7 sets of 2 apples is going to be 14. 7 sets of 6 oranges is going to be 42. So if we have 14 apples, we are going to have 42 oranges. And the reason that is happening is because at the beginning, we matched up a set of 2 apples to a set of 6 oranges.
As you saw in the video, we used the comparison of apples to oranges, talking about the comparison of apples to oranges. We had 2 apples per 6 oranges. So you looked at as it was increasing, so the ratio there was 2 to 6. Then we saw it was 4 to 12. Then we saw that it was again moving up, it was 6 to 18. So if you're looking at introducing it, we're not talking about inches to inches, apples to apples. We're talking about 2 different quantities in here, and having the students use the manipulatives to increase from 2 apples to 6 apples, oranges, 2 to 6. So therefore we're talking about 2 groups of apples to 6 groups of oranges. We're talking about a set of 2 to a set of 6. Based on the video that we had just viewed, when we looked at comparing sets to sets, sets of oranges to sets of apples, here is a problem that came from NAEP, and if you read the problem, it states a 4th grade class needs 4 leaves each day to feed 2 caterpillars. So I'm talking about the ratio of 4 to 2. I'm looking at 4 leaves to 2 caterpillars. So now the question is, how many leaves would it take to feed 12 caterpillars? So if we look at this problem as trying to construct the solution similar to that of what was done in the video, it would give the students the ability to use a manipulative to try to construct and reason through this problem. So let's take a moment to think about how would we solve the problem? How would we use manipulatives or even a piece of paper as before setting up some type of a table and having the students reason through this problem, where we're talking about a group of leaves of 4 to a group of caterpillars of 2. So the ratio is 4 leaves to 2 caterpillars, 4 to 2. So let's take a moment and think about the solution. Okay, if we look at the solution here, we can see that if it was mapped out, we have one group which has 4 to 2, the second group, which again is 4 to 2, the third group is 4 to 2. So we're looking at, if we look at the ratio of 4 to 2, 4 leaves to 2 caterpillars, we can now look at this table, count it up, and look at it to say that for 2, 4, 6, 8, 10, 12 caterpillars, I have 4, 8, 12, 16, 20, 24 leaves. So going from 4 to 2, I go 24 to 12. So as we look at this, a student might state or kind of recognize after doing some of these problems, I could have just taken the 4 and multiplied it by 6, because I have 6 groups of caterpillars, so that means I would have 6 groups of leaves, and the ratio of 4 to 2 would now become the ratio of 24 to 12. So again, looking at this, I'm not adding because I cannot add them. I do not have like denominators. I'm looking at a ratio of 4 leaves to 2 caterpillars. Again, looking at a comparison of groups where the quantities are not of the same dimension. Leaves to caterpillars, not leaves to leaves or caterpillars to caterpillars. So we're looking at the solution as a ratio, a rate of 4 to 2. For 4 leaves feeds 2 caterpillars. That's my rate. So getting the students before grade 6 to look at the ratio as a rate of, for 2 caterpillars, I need 4 leaves. It can be 4 to 2, or I can say it's 2 to 4, 2 caterpillars per 4 leaves. In a ratio, I can say 4 to 2 or 2 to 4. In a fraction, I cannot switch the numerator and denominator and have it mean the same thing. So there's another difference between a ratio and a fraction. Here's another problem that I have used, and I have also done this problem with students in elementary. I've used it in a graduate class that I've taught. So here's a problem, and it's a really nice problem that can be taken from the lower grades and built upon into the upper grades to be done in the 7th and 8th grade when they have more of an understanding what is a ratio and how to use a proportion. So here's a problem that could go across grade levels, giving different perspectives of the answer. So here's the problem. It says, during the night, a giant entered our classroom, and while groping in the dark for a light switch, the giant left a smudge that looked like a handprint on the wall. I've used this to state and to change the scenario a little bit by stating that we had a bag of cookies, and when we came in, our bag of cookies were gone, but here was a handprint, and the handprint was very large, so it had to be a very large person, so let's think about it as a giant. I've also had a handprint that was made for me that I taped to the wall. It's a large handprint, and I tape it to the wall, and I say, there's the handprint, and then let's look at it. How can we determine, based on the handprint, how big the giant is, or the person whose handprint this is? So this is actually a problem that comes out of the Ames series, and I've changed it up a little bit, and I've used, again, a hand that I've taped to the wall, and I made up a story. And as I stated, I have done this problem, and it works out really well. The children in the elementary grades just love it because it's curiosity, and it starts a conversation. I think that's an important part of starting a conversation of how am I going to solve this problem. And that goes back to the mathematical principles. How do I solve this problem? How do I make sense of what I need to do? What are the tools that I have to solve this problem? So let's think about how in the elementary grades we can get the students to come up with a solution to this problem. Let's look at a possible solution that could be done in grades 3 and 4 based on what we talked about in the video as talking about groups or sets of apples to oranges, looking at leaves to caterpillars. So if we have a child in the classroom, a student in the classroom, come up and put their hand on the hand that is drawn to the giant, here is a possible solution. We look at Holly. Holly puts her hand up on the picture, and 4 of her hands make one of the giants, so the ratio is 4 to 1. 4 of Holly's hands to 1 of the giant's hand, or it's 1 giant hand to 4 of Holly's hands. So again, we're talking about hands to hands, but we're talking about a comparison of not a part to a whole. We're talking about a comparison of 1 hand to 4 hands, or if we say 4 of Holly's hands to 1 of the giant's hands. Now we can start a discussion. How, based on the hands, can we talk about how tall is the giant? So they can kind of estimate and look at, well, could we look at my height as compared to hands? So it starts a discussion again. It starts looking at making sense of the problem. How can I reason the problem abstractly? So again, we're bringing in the mathematical principles to do this problem. Based on, without talking about what is a ratio, we're starting to get them to understand in grades 3 and 4 what is a ratio. It looks as a rate. 4 hands to 1 hand. 2 apples to 6 oranges. 4 leaves to 2 caterpillars. And as I increase the number of caterpillars, I have to increase the number of leaves. As I increase the number of apples, I'm going to increase the number of oranges. And again, it can be looked at as multiplicative, not additive. So there is a main difference again between a ratio and a fraction. A fraction has the properties of being able to add, subtract, multiply, and divide. A ratio you cannot add or subtract. They do have the principle of multiplication. Okay, now let's look at, starting in grade 6, what the Common Core talks about, what we should be looking at as a ratio, or the understanding, what are the standards for ratio in grade 6. So the first one is looking at understanding the concepts and use ratio reasoning to solve problems. So it's building upon what we looked at in grade 4 with our leaves to caterpillars to now bring it to a more advanced or a higher form of critical thinking. Also understanding the concept of a ratio and use the ratio language. We're now getting into the language of what is a ratio as a comparison of 2 quantities. I can look at, as I stated before, cookies to brownies. I have 3 cookies and 5 brownies, so my ratio is 3 to 5. Again, I'm looking at quantities. I have 10 trucks and I have 5 blocks, so my ratio of trucks to blocks would be 10 to 5. Again, I'm comparing 2 quantities. If I have 15 children in a classroom and 7 are boys and 8 are girls, I can say the ratio of boys to girls is 7 to 8. If I could state then the difference of what part of the classroom is boys, it's 7 out of 15. I'm not talking about, again, I'm talking about boys to girls, 7 to 8. And if I look at what part, it would be 7 out of 15 would be boys. So again, in grade 6, it starts looking at the language of the comparison of quantities of a part to a whole, or part to part, or group to group, set to set. So we're starting to get to look at the language in grade 6. Let's look at a problem that will start to distinguish between fractions and ratios in grade 6. Here we have a problem. This problem states in a bag of marbles, 3/5 of the marbles are blue and the rest are red. If the number of red marbles is doubled and the number of blue marbles stays the same, what fraction of the marbles will be red? Okay, if we look at this, we can change this up a little bit and ask what is the ratio of blue marbles to red marbles, and how will the ratio stay the same, or will it change? So let's think about that. Here's a problem talking about red marbles and blue marbles, and how we can change this problem also to talk about a ratio and show the difference between a fraction and a ratio of this problem. So let's think about how we would solve this problem. Let's take a moment and think about how to solve the problem. Okay, let's look at the solution. If we were given that 3/5 of the marbles in the bag are blue and the rest are red, then we know if we have 5 marbles in the bag, 3 are blue and 2 are red, so that tells us that the fraction of blue marbles is 3/5, the fractional part of red marbles is 2/5 in the bag. But we can also change this up, as I said before, to look at it as a ratio of stating that blue to red, blue marbles to red marbles is 3 to 2. I can also, as I said before, change the comparison to say red to blue, and if I say red to blue, then it's 2 to 3. So we're looking at comparing a part to a whole and part to part. So as a Fraction, the fractional part of red marbles is 2/5, while the ratio of blue marbles to red marbles is 3:2. So if we look at that ratio, if we double the number of red marbles in the bag, then the ratio is no longer 3:2, it's now 3:4. I still have 3 blue marbles, but I now have 4 red marbles, so it's 3:4. If we look at this, and another way of students to look at the distinction between a fraction and a ratio, if I add the 3 and the 4, that gives me the total that I have in the bag. I have 7 marbles in the bag now. If I added the 3 and the 2, I had 5. That gave me my total, 3:2. So now I have 3:4. I have 7 marbles in the bag. So now if I wanted to know what the fractional part of blue marbles in the bag are, it's 3/7. And if I wanted the fractional part of red marbles, it's 4/7. So therefore we're looking at being able to compare a ratio, the concept of a ratio, and the concept of a fraction, part to whole and part to part. And looking at that, if I look at, here is this habits of mind, getting them to look at this process, that the 3:2 tells me there are 5 marbles in the bag. The 3:4 tells me there are 7 marbles in that bag. That's my ratio. So again, looking at part to part, whole, part to whole. So the distinction between what is a ratio and what is a fraction. What I'd like to do now is to show you a video, again, using concept of ratios, but as it was stated in the Common Core standards, to start talking about the language, getting the students to understand the language that is appropriate. So let's look at this video, and then it gives you another perspective of introducing ratios using not only the concept but now the language.
We're going to look at matching things in an unequal fashion. In this example, we're going to use apples and oranges. And what we're going to do is we're going to match 2 apples for every 6 oranges. So let's record that. We have 2 apples, and we're going to match that with 6 oranges. Let's get another set of apples and oranges. So we're going to have a set of 2 apples and another set of 6 oranges. So now we have 2 sets of 2 apples and 6 oranges. We have one here and we have one here. But another way of looking at this is that we actually have a total of 4 apples and a total of 12 oranges. So what we're going to do over here on our mat is record the total. We're going to record the totals as they appear on our work mat. So now we first had a total of 2 apples and 6 oranges. We now have a total of 4 apples and 12 oranges. Let's do it again. We put another set of 2 apples and we put another set of 6 oranges. So now we have 3 sets of 2 apples and 6 oranges. We have one set here, one set here, and one set here. But over on our recording, let's record the total number of apples and the total number of oranges that we have. With the apples, we now have 6 apples, and those 6 apples match 6, 12, 18 oranges. So 6 apples match 18 oranges. Now let's look at a problem. What we want to do is we're going to develop a set of 14 apples, and we're going to find out how many oranges we need to be shared out unequally to match those 14 apples. So what we're going to do is we're going to create our set of 14 apples. we have 6 already. I add another 2, that gives us 8, and I can record the total number of apples there. I put another set of 2 apples, that gives us a total of 10 apples. I give another set of 2 apples, that gives us a total of 12 apples that I record in the totals. And finally, I get to my 14 apples, which I want to have, and I'm going to record that in my totals. Now the question is, how many oranges do I need to match up with these 14 apples? So let's start adding sets of 6 oranges. I add one set of 6 oranges. I have 8 apples here, and I will have 6, 12, 18, 24 oranges. So 8 apples matches 24 oranges. I match up another set of apples and oranges. I have 2 apples here. I match it up with another set of 6 oranges. So now on the left, I have 2, 4, 6, 8, 10 apples right there. And that's going to match up with 6, 12, 18, 24, 30 oranges. So 10 apples match 30 oranges. Again, I'm going to add another set of 6 oranges to match up with this set of 2 apples. So now I have 2, 4, 6, 8, 10, 12 apples right here. That's my total number of apples. And the question is, how many oranges do I have? I have 6, 12, 18, 24, 30, 36 oranges. And finally, I add in another set of 6 oranges to match my last set of 2 apples. Now I have all 14 apples as a total. And the question is, how many oranges do I have as a total? 6, 12, 18, 24, 30, 36, 42. I have 42 oranges. So, if I want 14 apples, and I'm giving out the apples and oranges, a set of 2 apples for a set of 6 oranges. If I have 14 apples, I need 42 oranges to match up with my 14 apples. And again, the reason for doing that is that I'm handing out the apples and oranges at a rate of 2 apples for every 6 oranges.
As you saw in the video, we started to take the concept that we demonstrated in the first video and take it to the next level, as we talked about when I started the webinar of looking at the model of 4, looking at the kinesthetic, now taking it to introduce the language so that the students are being able to talk the mathematics. So this is an important part when we start teaching, not only to be able to do it, to be able to talk the mathematics, the language of mathematics. So that video was a demonstration of how we can now go from the first step in our model of how to teach mathematics to the second step, the more hierarchy. We're talking about the hierarchy and being able to teach mathematics. Let's continue to look at the standards for ratio in grade 6. Now they're asking to have the students understand the concept of a ratio as a unit of rate. Also being able to look at a different way of writing a ratio of 2 to 3, not using the division sign, but to use the colon when you're talking about a comparison of a quantity of, as we saw with the marbles, 3 blue marbles to 4 red marbles when we increased it by a multiple of 2. Also, again, understanding that the denominator cannot be 0 because, as I stated before, every fraction is a ratio, but not every ratio is a fraction. But you still have to adhere to the fact that we cannot divide by 0. So the comparison cannot be to 0 if it's in the denominator. And again, starting to be able to look to solve real-world problems using ratios as rates. So again, looking at being able to develop this concept, and as they're stating, looking at it through tables, diagrams. In the videos, you saw that we took this and we used basically a table lining up the apples to the oranges and increasing it at a rate. So increasing it. So again, using that multiplicative property of being able to increase the ratios. So again, here we're looking at being able to use a visual to be able to solve these problems and get the students to have a fundamental understanding of the concept of a ratio as a rate. Okay, let's look at a problem again. Here's a problem. John and Will ran for 6th grade class president. There are 36 students voting. John got 2 votes for every vote Will got. How many votes did each get? So again, we're talking about a rate, the rate of 2 to 1. For every 2 votes that John got, Will got 1. So now we have to look at determining how many votes did John get and how many votes did Will get in order to solve the problem. So let's think about, if we look back at the standard, how we can do this with a diagram or even an equation, but let's first look at it by stating, let's look at it through a table or through a diagram. So let's take a moment and think about how we could solve this problem by using a diagram to solve this problem. Okay, let's look at the solution by making a table, a diagram. So one approach, as we can see here, is to use a ratio table that has a column of votes for Will, a column for votes for John, and a column for the total. Previously, when we were talking about the marbles, I stated that if you looked at the ratio of 3 to 4, that told me I had a total of 7 marbles. If I looked at the ratio of 3 to 2, 3 blue marbles to 2 red marbles, I had a total of 5. So we're using that concept again by setting up a table. If Will got 1 vote, then John got 2 votes. That's a total of counting for 3 votes. If Will got 5 votes, because the ratio is 1 to 2, and if I use that multiplicative identity, a multiplicative reasoning, so here we can state that if Will got 5 votes, then John got 10 votes, and that's the count for 15 votes. If Will got 10, John got 20, that accounts for 30 votes. 11 to 22, that accounts for 33. 12 to 24, that accounts for 36. So if I were going to ask another question here, what part of the votes did Will get? He got 12 out of 36. What part of the votes did John get? He got 24 out of 36. So we can look at getting the students to understand the rate of 1 to 2 for every 1 vote that Will got, John got 2, and then looking and taking it, what part of the votes, what fractional part of the votes did Will get, what fractional part of the votes did John get. Again, getting them to distinguish between a ratio as being the rate, comparing part to part, and the fraction as comparing the part to the whole. So in making a table like this, it gives the students the ability to start to make that distinguishing property between part to part, whole, part to whole, and again, using the mathematical properties of principles, again, the habits of mind, looking at being able to reason with this abstractly. So here we're looking at a solution and as the standards had asked, or starts to ask us to do, look at tables of equivalent ratios, diagrams. So here is a solution using a table to come up with a solution of how many votes did John get, how many votes did Will get. Okay, here, let's look at this diagram. If we presented the students with this diagram, this is a line diagram, you can see that we're talking about 3 cups. Each rectangle represents a cup. We're talking about 3 cups of apple juice, 2 cups of grape juice. If we mix them together, we can say that in our mixture, the ratio of apple juice to grape juice is 3 to 2. 3 to 2. If we talked about the total number of cups in the mixture, there are 5 cups. So the apple juice is 3/5 of the mixture. The grape juice is 2/5 of the mixture. But when we talk about the comparison of apple juice to grape juice, we're talking about the ratio 3 cups of apple juice to 2 cups of grape juice. So if I wanted to double my mixture, I would have to use, thinking about the videos that we viewed, and looking about at the table in the previous problem, I would look at it to state if I wanted to double my mixture, I would need 6 cups of apple juice, 4 cups of grape juice, because the rate has to be the same. So I am now increasing my rate. I am stating that 3 to 2 would be the same as 6 to 4. They are equivalent. It's in the same ratio, the same proportion, the same. We're now starting to get the students to think about bringing this to the next level, the proportion of apple juice to grape juice and keeping the equivalence. So we're looking at this to total of this and how it represents. So giving them a diagram, again a picture to look at. If I wanted to make 4 of these mixtures, again, how many cups of apple juice would I have? How many cups of grape juice would I have? So looking at if I have a ratio of 3 to 2 for one mixture and I wanted to make 4 of these mixtures, how many would I have? I would have to have 12 cups of apple juice and 8 cups of grape juice. So again, looking at that 3 to 2, 12 to 8. So again, it's getting the students to be able to, as in the video, they can use the manipulatives, they can think about using the multiplicative, how we can do this. So here are ways to develop tasks that will get the students to understand the concepts of a ratio. As we continue to look at the standards in grade 6, we will see that they continue to talk about a ratio as being a unit rate, so solving problems with unit pricing and constant speed, being able to find the percent of a quantity as a rate, as per 100, using ratios to solve and convert measurement units, manipulate and transform units appropriately when multiplying or dividing quantities. So we're going a little bit further into, again, explaining that a ratio is a rate. So looking at it, as we looked at in the last problem, it kind of unified the fact that when we start looking at comparison, I was comparing juice, but 2 different types of juice, apple juice to grape juice. And if we wanted to talk about it, we talked about the juice and the proportions of each different types of juice within it. So now we're going to take this and start to look at maybe what percent of the mixture was apple juice, what percent of the mixture is grape juice. So again, looking at it as a rate, as a part. So this is taking it now, and as the Common Core standards is talking about, focusing on the standards by the coherency of let's take it and build upon it and let's move forward. So we're extending our concepts and our knowledge of what a ratio is. Let's look at another problem, another task. Here's the problem. Alice, Raul, and Maria are baking cookies together. They need 3/4 cup of flour and 1/3 cup of butter to make a dozen cookies. They each brought the ingredients they had at home. Alice brought 2 cups of flour and 1/4 cup of butter. Raul brought 1 cup of flour and 1/2 cup of butter. Maria brought 1 1/4 cups of flour and 3/4 cup of butter. If the students have plenty of the other ingredients they need, the sugar, the salt, the baking soda, and everything else, how many whole batches of a dozen cookies can they make? Well, the ratio here, if we're looking at this problem, is 3/4 cup of flour to 1/3 cup of butter. So there's the ratio. So if we look at all of the ingredients, how can we maintain that ratio of 3/4 cup of flour to 1/3 cup of butter in order to make these cookies? So let's think about how using that ratio and using everything that we've talked about so far to look at how to solve this problem. So let's take a moment to think about how we would solve this problem in coming up with how many batches of a dozen cookies can be made from the ingredients that all of the students brought from home. So if we look at the solution and we total up all of the flour that was brought in by the students, it totals to 4 1/4 cups of flour. And if we look at the amount of butter that they have, if we total up the butter, it's 1 1/2 cups of butter. But remember, we have to keep the ratio of 3/4 cups of flour to 1/3 cup of butter. So in looking at this, we have to determine how many 3/4 cups of flour are there in 4 1/4 cups. So we're looking at how many 3/4 cups of flour are contained in 4 1/4 cups of flour, the total flour that they have. So if we do the mathematics there, we'll see that just based on flour, they could have 5 2/3 batches of cookie based on just the flour. Now let's look at the butter. They have a total of 1 1/2 cups of butter. Now we have to ask ourselves, how many 1/3 cups of butter are there in 1 1/2 cups of butter? So again, doing the mathematics, we find out that based on the butter, we can do 4 1/2 batches of cookies based on the amount of butter that we have. Since the ratio has to be 3/4 to 1/3, we notice that because of the amount of butter, we can only make, the butter is the limiting factor here, and we can only make 4 dozen cookies, 4 batches of a dozen cookies. Although we have enough flour for more, the limiting factor here is the butter. So this is a problem where we really have to analyze the data and look at keeping that ratio of 3/4 cups of flour to 1/3 cup of butter. How many can we make? So in doing all of the math, and again, we're using fractions here, we're adding fractions, we're dividing fractions, and then we're looking at the ratio of flour to butter. So the final answer then would be 4 whole batches of a dozen cookies. I'd like to revisit the video again, and as we look at this time, the first one was the kinesthetic, then we went to the level of language, now we're going to look to the level of connecting this. So let's look at this video again in a different light and it's a different presentation of how to, again, look at teaching the ratios for the different standards of the real world problems, looking at, again, talking about units and rates. So let's look at this again in this time for connecting the concepts.
We're going to match things in an unequal fashion. In this example, we're going to match up apples and oranges. And we're going to match them up in the following way. We're going to match up 2 apples with 6 oranges. And we're going to record that. So we're going to record that we have 2 apples and 6 oranges. Let's do that again. We're going to take another set of 2 apples and another set of 6 oranges. So now we have 2 sets of 2 apples and 6 oranges. We have a set of 2 apples and 6 oranges here. We have a set of 2 apples and 6 oranges here. But there's another way of looking at this. Here we have a total of 4 apples. Here we have a total of 12 oranges. And what we're going to do on our SmartPal is we are going to record the totals. So we're going to have 4 apples and 12 oranges. Let's do it one more time. We're going to have a set of 2 apples and we're going to have a set of 6 oranges. So now we have 3 sets of 2 apples and 6 oranges. We have one here, we have one here, and we have one here. We can also look at the total. The total number of apples is 2, 4, 6. So let's record that. The total number of oranges is 6, 12, 18. So let's record that. So we're sharing out things, a set of 2 apples and a set of 6 oranges. Now what happens if we want 14 apples? How many oranges would match up with 14 apples? So let's create the 14 apples. There's 8. There's 10. There's 12. And there's 14. So there are my 14 apples. And the question we wish to ask is, how many oranges will match up with my 14 apples? So let's put a box here. That will be the number of oranges that will match up with my 14 apples. Now let's look at this. We have 14 apples, and I'm matching those up with my box. I'm doing that in the same way that I matched up my 2 apples with my 6 oranges. And to separate them, I'm just going to use the line. But since I'm matching them up in the same way, I can put an equal sign in here. I'm matching up my 14 apples to a certain number of oranges in the same way that I'm matching my 2 apples with 6 oranges. Now let's look at the arithmetic. In order to go from 2 to 6, I can multiply by 3. So 3 times 2 gives me 6. That means in order to go from 14 to my number of oranges, I can also multiply by 3. So now the question is, how many oranges do I have to match up with 14 apples? Well, 14 times 3 is 42. So that means that if I'm matching up apples and oranges at a rate of 2 to 6, and I want to find out how many oranges match up with 14 apples, my answer is 42 oranges. And the reason all of this is happening is because I'm matching up my apples and oranges at a rate of 2 to 6.
So we looked at this video again for the third time, showing the different levels at which we can present the mathematics: the kinesthetic, the language, connecting. Okay, let's look at the video one last time to show the fourth stage of the mathematics, the symbolic, how we can bring it to the symbolism, which math, as I tell all my students, math is a language of symbols. So how do we bring and we connect the concepts? How do we connect that a ratio is a set? We've been presenting this as looking at a set of apples to a set of oranges, a group of 2 to a group of 6. So let's look at the last video to see how it comes full circle to represent the symbolic.
We are looking at how to match things up when we distribute them or give them out in an unequal fashion. And so in this example, what we're going to do is we're going to talk about how we give out apples and oranges. And what we're going to be doing is we're going to be giving out a set of 2 apples for every set of 6 oranges. So every time we give out 2 apples, we're going to give out 6 oranges. And the question is, suppose I want to give out 14 apples. How many oranges? And I'm going to put a red box here to represent the number of oranges that I would get if I had 14 apples. And remember, we're giving out apples and oranges in a way where we give out 2 apples every time we give out 6 oranges, or we give 6 oranges every time we give 2 apples. So what I can do is I can compare the way I give out the apples and the way I give out the oranges, and those are going to be the same. So my 14 apples are related to so many oranges, that's what I'm trying to find out, in the same way that 2 apples, a set of 2 apples, is related to a set of 6 oranges. Now I know I can take 2 and multiply it by 3 and get 6. So I'm going to do the same thing with my 14. I'm going to take my 14 and multiply it by 3 and see if that helps me find the number of oranges. So my box then, or my unknown, or the number of oranges that matches up with 14 apples, is going to equal 14 times 3. So the number of oranges that matches up with 14 apples, which is represented by my box, equals 42 oranges. And the reason we get 42 oranges is because at the beginning we stated that we were giving out 6 oranges for every set of 2 apples. So the answer then is 42 oranges match up with 14 apples.
Okay, as you've seen in the video, we went through the 4 stages, starting with the first video of the kinesthetic, the language, connecting, and now the symbolic. And again, we were using apples to oranges, talking about sets, groups of sets. And again, in the last one, you could see again, a student could recognize the pattern that this was, you can multiply as we increase the steps because it was continuously increasing by a constant ratio. As we move forward, in grade 7, we start to see that when we look at the standards, they start to introduce the word proportional, analyze proportional relationships, use them to solve real world and mathematical problems, compute unit rates. Again, we're talking about rates with fractions, including ratios of lengths, areas, other quantities measured in like or in different units. Again, different units would make sure that it is a ratio like units. It could be converted to a fraction as a part to a whole, part to part. Different units, it's part to part. So again, we're building. Again, the focus of the standards is to focus on them, to bring them and moving forward. So here again, recognizing the relationship of proportions. So we're now introducing a broader picture of a ratio as being a proportion, and again, bringing it back to solving it in real world. So if we go back to what we look at, what is a proportion? We're using this word proportion. What is a proportion? A proportion can be written as two equivalent fractions. It can be two ratios which are equal. So a proportion can be written in many different ways, as we stated before. If we look at the notation, 3:2, 3 to 2, we can write it as 3/5. That is a ratio. So therefore, we're now talking about a proportion, and we're saying that a proportion is written as two equivalent fractions. If we go back to our videos, we could see that if we looked at the groups of apples to oranges, we had 2 apples for 6 oranges. We had 6 apples to 18 oranges. And if we look at that ratio of apples to oranges was constant, that consistent rate of change, increasing it by the constant rate, incrementing the apples by groups of 2, incrementing the groups of oranges by 6 every time we added another group. So we're now looking at the proportionality of 2 is to 6 as 3 is to 18. So in grade 7, we're now taking the concept of ratio and bringing it to the next level. As we move on in grade 7, the standards look to decide whether 2 quantities are in a proportional relationship by testing for equivalent ratios. The common theme through all of this seems to be that when we talked about fractions on the last webinar, and when we're talking about ratios, and we're talking about proportions, the common theme keeps looking at going back to a visual, a table, a graph, a coordinate plane, looking at how we can get students to visually understand the concepts, to draw a diagram, to be able to explain. This is, a new focus in our standards of having the students not just do the procedural, but to be able to explain why. And they're doing it through, again, pictures, diagrams. As we saw in the videos, we used manipulatives. Those manipulatives start to give them the feeling of being able to draw this, manipulate, looking at how I can explain, remembering, not just memorizing. It's that habits of mind, looking at how I can do this, analyzing the data, and how I can build it into a table or a graph. So that seems to be this common theme through the Common Core standards, looking at the visual so that students can explain their work, whether it's in the language or it's in the symbolic. So it's that ability to explain, demonstrating understanding. The Let's go back and revisit the problem, the hand of the giant. As I stated when we first looked at the problem, that is a problem that you can use at different grade levels because you can add more and more advanced mathematics to it. So if we look at this possible solution and setting up a ratio of a proportion and then to a proportion, here if we measure, we say that Juan's hand is 15 centimeters. The giant's hand, if we measure it, is 60 centimeters. If we know that Juan is 147 centimeters tall, how could we find the height of the giant here? A little bit differently than when we did before. We talked about the ratio of 4 hands to 1 hand. We're now talking about the length of Juan's hand to his height as the length of the giant's hand to his height. So we can set up two equivalent fractions to give us a proportion. We could state that 15 is to 147 as 60 is to that unknown quantity. So we're looking at how we can set this up. We could always say that we're looking for an unknown, and it's starting to get them to realize of being able to solve a very simple equation. It's getting them again looking at more involved mathematics. So here's the problem of how we could solve this. Another solution, another possible way of solving this problem, again, by looking at the length of the hand to height. So we're talking about keeping it in the same ratio by setting up a proportion. And if we look at one more possible solution, here is a solution that uses basically a line graph where we're looking at setting up the hand to the height by using measuring tapes, and again looking again to set up a proportion of hands to height. So these are possible solutions of looking at setting up a proportion, knowing the rate of change. We're continuing with grade 7 and looking at the standards. In addition to the hand of the giant problem, there was another problem that I have done with some of my classes. It's a classical problem that was in NCTM. It's called the Bigfoot problem, and it's similar to the giant problem. It looks at creating a foot, again, of large size, and asking the students to solve the problem based on the size of the foot. How can we determine the height of the person who has that size foot? So it's another offshoot of this type of a problem. It's very similar, because if we look at the continuing with the standards in grade 7, we talk about representing proportional relationships by equations. The Bigfoot problem talks about setting up an equation, again, measuring the size of the foot, measuring the size of the foot of the student, looking at the height, but here again, could bringing in the concept of the height be affected by the size of the foot? This is a way of testing students who have different size of length of their foot to their height, and this talks about setting up these equations. Are these proportions constant? And this brings us to plotting these points, the size of my foot to my height, the size of another student's foot to their height, and starting to plot these points on a Cartesian plane using the ordered pairs and looking at, is this rate pretty consistent? Are they equivalent? Looking at this proportional relationship and paying attention to the rate of change, the rate of increase here. And again, being able to explain what this proportional relationship means along a graph. This is actually the prelude to when we start to look at graphs and we start to look at this concept of this constant rate of change. So in grade 7, they're starting to have the students talk about this unit rate of change, explain what it means in looking at point on a graph, this special relationship of looking at now again another type of a visual. This visual is now looking at a graph. Let's look at another problem that would look at these concepts. So if we look at this problem of who's got speed, this is a problem. Not only have I done this problem with students in middle school, high school, and my graduate class, I've also done this problem in my college classes. Here, again, John and Mike were discussing who had the faster car, so they decided to have a drag race. They lined the floor with Unifix cubes and a tape measure to mark the distance the car traveled per second. Starting the cars at the starting line, they then began to record the distance per second as measured by the cubes. Use the following data to determine whose car has more speed. Draw a graph to validate your answer. So again, we're looking at creating distance over time, and that's starting to talk about this rate of change. I've done this problem with using 2 battery-powered cars, which would give you the constant rate, but when I introduce it in an algebra class at the college or my calculus class, I use 1 battery-powered, 1 non-battery-powered car, push car. Again, and that would show the differences and that it's not, I cannot set up an equivalent proportion here. One is constant, one is not constant. So in looking at the different units here, that would be maybe a way to talk about the different units. But starting out using 2 battery-powered cars and putting this problem into action, where you can have a stopwatch, and you have groups doing this problem, this activity, who's watching, counting the Unifix cubes and then measuring. So here is a nice way to start talking about that constant rate of change and looking at this activity to measure the distance that the car has traveled in relationship to the time. Okay, here is some data that students might get something similar to this, something different. But here is a way of looking at the data, setting it up into a table, and we look at it as John's car, and the distance it traveled in 5 seconds, Mike's car, the distance it traveled in 5 seconds. We see that John's car traveled 3.2 inches in 1 second, 6.4 in 2, 8 in 2.5. Well, based on all the work they've done with ratios and this constant rate of change, could they, not knowing if a student missed the distance at 4 seconds, could they fill that in? And there it is at 5 seconds, it traveled 16 inches. Here looking at Mike's car, traveled 3.8 inches in 1 second, 7.6 in 2, and so on. And again, someone missed it at 4 seconds. Could we fill that in? Looking at the information, looking at the patterns, this constant rate of change, how it's changing. This is starting to, if we graph this, looking at the line, the graph, which is steeper, this starts them thinking about this constant rate of change. In the webinar that we will do with on algebra, we will revisit this as being defined as that slope, that constant rate of change. So getting students to understand proportionality starts to get them to understand later on that concept of slope, that constant rate of change. We're looking at a rate of change here, this unit rate of change, looking at a graph, being able to interpret a graph. So if we looked at this graph and we started to plot the data, interpreting a line, looking at the table, we can see which car went faster. We're looking at the change in the differences. Again, starting to show that the change in the differences is constant, that concept of slope. looking at the interpretations of the table, interpretations of the line if we graphed it, and it all goes back to the interpretation of how I'm looking at this data using the mathematics of a ratio and a proportion to solve my problem. So it starts to lead to the equivalence of ratios as a proportion. It starts to lead to what is the rate of change, what would the slope be as that rate of change. So this afternoon I was hoping that I've given you some ways of looking at ratio and proportion, some problems, ways of answering those problems, looking at the concept, the standards to bring those concepts through activities, looking at these activities. So this is some of the tasks of how we could present these ratios and proportions to our students. Again, hands-on, very, very visual, very kinesthetic, and then taking that and being able to look at the language, how do I talk about it, because that's an important part of the task when they're going to start taking these tests. The language, how do I put it all together, making the connections, and of course the symbolic. What do the symbols mean and what do they represent? So that's the webinar for this afternoon, and I hope that this has given you a new way of looking at, or a clearer way of looking at, ratio and proportion. Thank you for attending the webinar this afternoon. If you have any questions or comments, you could email Frank Gardella or myself, and we would gladly answer any of your questions. We'd like to hear any comments. So thank you for attending this afternoon. Thank you, and I hope that, again, that I gave you a way of looking at and presenting ratios and proportions. Thank you.